I would sit down, as soon as I get a blank test, I would write down the formulas I need to know. So remember, only if you see the keyword compounding continuous do you use the formula PERT, correct? Yes. So you'd say this is y equals p times e raised to the RT. And remember with PERT, you don't change you do change it to obviously a mathematical decimal, but you don't add the 100%. You know what I'm talking about, the percent. So our put down amount is 200, isn't it? E is a number, E is E. Our rate is 0.08. Don't put 0.8, that'd be 80%. And then the time in the account is 10 years. How much money does this person have? 11 cents-ish. Okay, awesome. So they made decent money, I mean better than zero. Now it says if the interest is compounded bi-monthly, so you'd say, well, this one's not the one that's just easy, straightforward to write. It's the one with the ugly formula, right? So that's y is equal to p times by 1 plus r over n raised to the nt. P is the put down amount, so 200. 1 plus 0.08. With this formula, you also don't add the 100%. N is the number of times it compounds in 1 year. So doesn't it bi-monthly happen twice a month? So in a year, it's going to happen 24 times, and then raised to the 24 times 10. You calculate it, and you get... So notice it's not a huge difference from getting interest all the time versus twice a month. It's not a huge difference, and we talked about why last time, because exponentially, it finally it just starts growing up kind of at that same rate, right? It kind of tops out. We talked about that. Okay, awesome. Were you able to get them right? Okay, awesome. Okay, let's review the one-to-one property from last time. So it says use the one-to-one property to solve for x. So remember, the one-to-one property says if you can rewrite these both as the same base, you can just solve using your exponents because they're both base 3. So let's look at this. Base 3 to the what power equals 1 over 27. I'm going to point something out. Isn't 1 over 27, 27 has obviously been flipped over a fraction, hasn't it? So doesn't that mean that the exponent was negative? Yeah. So let's just pretend this was base 3 to the x equals 27. Let's say it wasn't flipped. Let's figure out what base 3 this would be. Base 3 to the x equals base 3 to the what? Third. Right, everybody? So you say, but it wasn't just 27, it was flipped. So isn't this going to be negative 3 for that? Yeah. So then the one-to-one property allows us to solve using our exponents. So isn't the true statement x equals 3? Sorry, x equals negative 3. Do we have questions on that? All right. I want you to do the next one by yourself. Everybody, use the one-to-one property to solve with your exponents. So you need to write them both as the same base. I personally would rather flip and not have fractional bases. So ready, go. Do that second one. Everybody shout out your answer. Negative 5 is correct. So you'd say, isn't this base 3 to the negative 1 raised to the x plus 3? Do you agree? Equals base 3 to the second. Now from there, you distribute your negative because raise a power to a power and you multiply. So negative x minus 3 equals 2. So then you would add 3. Negative x equals 5, and then divide both sides by negative 1. So x equals negative 5, people. All good? Okay, very good. Moving on to today's lesson. So this is actually 5-2. In the previous year it was unit 7 for some reason. Okay, 5-2. We're going to be dealing with today just the very, very basics of logarithms. Guys, the basics of logarithms are super easy. As long as you understand what's going on, probably one of the easiest lessons of the year. So first of all, last time we learned how to graph y equals base 2 to the x, didn't we? So we know this is an exponential function because x is in our exponent. And then look, I made an xy chart here, my blue xy chart, and I plugged in values. If I plug in negative 3, we know it doesn't make it negative, it just flips it, making it a really small decimal, 1/8. If I plug in negative 2, I get 1/4. If I plug in negative 1, I get a half. If I plug in 0, I get 1. If I plug in 1, I get 2. And if I plug in 2, I get 4. So I have graphed my exponential function. Do you agree? Yeah. Which remember, the more we plug in negatives, the closer, the smaller the decimal gets, so we're approaching 0. So remember, we have this horizontal asymptote at 0 here. Do you agree? All right. Now, if I said to you, given these blue xy points, find the inverse. Can anyone remember a couple units ago how we find the inverse of an xy point? You flip them. So I literally took my xy points and I flipped them, and now I've written them down. Look. And I've graphed it. Over an 8, down 3 units. Check, right there. You guys see? Over a 4th, down 2 units. Over a half a unit, down 1 unit. Over 1 up 0. Over 2 up 1, and over 4 up 2. You have just graphed a logarithm. Logarithms and exponentials are inverses of each other. The red thing is a logarithmic function. So really not that hard, right? If you know how to graph an exponential, you know how to graph a logarithm. So I'll tell you what the logarithm form is for this. This red thing is, if this is base 2, it's going to be log to the base 2 of x. Y equals log to the base 2 of x. And next we're going to learn how to switch back and forth between logarithmic and exponential form. But you see how it's base 2, base 2? These are inverses of each other. Alright, so this is where you'll start writing down. So like I just said, a logarithm is the inverse of an exponential, and an exponential is the inverse of a logarithm. So we can literally take and rewrite something from a logarithm to its exponential form, and we can take something from its exponential to its logarithm form. They're equal. So, everybody writing this down. This logarithm reads, y equals log to the base a of x. Now, technically, a lot of books don't put parentheses around the x, but technically it's like, that's what's creating up the function. So it's of x. So this, everybody say it with me. You have to be able to say it right. So this is log to the base a of x. Now this base a is written kind of small and tucked in right here close to the logarithm. So this reads, one more time everybody, log to the base a of x. Okay, now this is the logarithm form and this is the exponential form. So look at the exponential form. This is base a to the y equals x. Now really I should switch this. Isn't it true that for an inverse don't we switch x and y? So it actually, I still haven't done that yet. I need to switch x and y. So really I should be writing it as base a to the x equals y. Logarithms to the base a undo base a's. Base a's undo log to the base a's. Inverses undo each other. Doesn't addition undo subtraction? Multiplication undoes division. And square roots undo squares. Log base a's and base a's are just like that. They undo each other. So let's see how to switch back and forth. Okay. Here is a true statement here. Log to the base 3, technically of 9. Once again, it goes without being said, there are parentheses there. Log to the base 3 of 9 equals 2. Well, why is that? Because base 3 squared equals 9. Now, we're not solving anything. Look, it's already solved. Isn't 3 squared 9? Yeah. That's just, this is the logarithm form of base 3 squared equals 9. So let's see how I can algebraically switch back and forth. It's actually quite simple, so watch. I just told you inverses undo each other, which we already know. We just learned that base 3's undo log base 3's, and log base 3's undo base 3's. So if I said to you, I need you to write this in its exponential form, you'd say, okay, if that's true, I need to get rid of the logarithm. This is log base 3. What undoes log base 3 is base 3. Now, if you do it to this side of the equation, you have to do it to this side. Just like when you add things, don't you have to do it to both sides of the equation? So I'm doing base 3 both sides. Well now, base 3 and log to the base 3 cancel out. That's what inverses do. They undo each other. So now do you see how 9 drops down? So then we have 9 equals 3 squared. 9 equals 3 squared. And it's written in its exponential form. So let's go the other way. If I said take 3 squared equals 9 and write it in its logarithmic form, you'd say, okay, I need to undo base 3 because I need it to be a log base 3. So what undoes a base 3? A log base 3. So you would log base 3, both sides of the equation. Now a logarithm entraps, like it eats the other side. So this is like this, log the base 3 of base 3 squared. So what happens is base 3 and log the base 3 cancel out because that's what inverses do. So 2 drops down. 2 equals. Now on this side, you see how I have a log to the base 3? I have a log to the base 3, and then it's like eating or entrapping 9. I've just written it in its its logarithm form. So we can switch back and forth. We're not solving anything, we're switching back and forth. Okay, let's do this one below it. Oopsies, I didn't mean to do that. Okay, if I said to you 5 to the 3rd power equals 125, that's true, correct? Well, write it in its logarithm form. So how did I get here? Let's see. What would I do? Log base 5 both sides of the equation, because that would undo base 5. So now look, on this side, log the base 5 and base 5 cancel out, don't they? So 3 drops down. So 3 equals, and then on this side, understand how a logarithm works. This is log to the base 5, and then it's eating, or like of, 125. And now you've just written it in its logarithm form. Okay, everybody? Pretty easy, right? Okay, so let's go this way. If I said rewrite this in its exponential form, you would do what? Base 5 both sides. Base 5, base, do you get what I mean by base? It's not times by 5, it's a base. Yeah. So base 5 and log of the base 5 cancel out, so 125 is now out. And then we have base 5 to the third power. And you know you did it right, it's a true statement. Make sense, everybody? Okay, cool. Logarithms and exponentials are equivalent. So if I said to you, evaluate log the base 2 of 32, that means calculate me. We have to not do it without it. We can't do it in a calculator. We need to not do it in a calculator. So I'm asking you to evaluate this. It's a lot easier to evaluate logarithms as an exponential a lot of times. So what I'm going to do is say, well, I'm going to make this an equation, even though it's technically not. I'm going to say I have no idea what it's equal to, so equal to, I don't know, question mark. And now what I'm going to do is rewrite it in its exponential form, and then I'll solve that way. So let's undo log to the, because this is really log to the base 2 of 32, like that. So you'd say I'm going to base 2 both sides. So now isn't the true statement 32 equals base 2 to the question mark? Does everybody see my new true statement? And that's a lot easier to solve because we know the one-to-one property. So 2 to the 5th equals 2 to the question mark. So doesn't it equal 5? Yes. So you'd say log the base 2 of 32 equals 5. It does. It simplifies to be 5. It calculates to be 5. Make sense? Pretty straightforward. Okay, so let's set this one equal to, we don't know what it is, so equal to question mark. So what would be my true statement? What would be my true statement if I rewrote it as an exponential? 1 equals 3 to the question mark. Does everybody see? And base 3 in both sides. Ding ding, those cancel out. Okay, any base to what power equals 1? 0. So log the base 3 of 1 equals 0, everybody. Okay, let's do another one. Log the base 4 of 2, you'd say equals, I don't know, then wouldn't we base 4 both sides? 2 equals base 4 to the question mark power. 4 to the what power equals 2? 1/2. Very good. The square root of 4 equals 2. So log the base 4 of 2 equals 1/2. Very good. Okay, do this one by yourself. If you need to rewrite it in its exponential form, great. That's why I taught it to you. So ready, set, go. Everybody do that bottom one. I'll scroll up to the people in the back. So log the base 10 over 1 over 100 evaluates to be -2. Does anybody have questions on that? Okay, good. If you wrote it as an exponential, it's flipped over a fraction, right? You guys okay over here? Okay, awesome. All right, let's keep going. All right, write these down. Here are basic properties of logarithms. These are just the basics, and they're really straightforward. You have to know these and be able to simplify them like that. This is one thing a couple years ago, the calculus teacher came to me and said, the kids are not remembering the very basic properties of logarithms. You've got to hit that hard. So, these are very basic, and you need to know them like this, like in the snap of a finger. So everybody writing it down. Log to any base of 1 will always equal 0. It'll always simplify to be 0. Now, why is that? Well, because isn't any base to the 0 power 1? Yes. Well, if that's true, then log any base of 1 will always simplify to be 0. So let me ask you, what's log the base 5 of 1? 0, people. I just said log to any base of 1 is 0. Let's try again. Log the base 2 of 1 is 0. Log the base pi of 1 is? Log the base smiley face of 1 is? 0. Okay, you guys get the rule. Sweet. Moving on to the next rule. Log the base a of base a will always simplify to be 1. And that's because, isn't a to the first power a? Yeah. Or, honestly, it's a lot easier for me to just think of this as this. Isn't this log the base a of a to the first? Don't logs and bases undo each other? So 1 would be what it would simplify to be. Agree? It's a lot easier to think about, I think, that way. So this makes sense then. Look, log the base a of base a to the x. Won't those cancel out? Giving me a x, right? So it's pretty easy. Well, then also, base a raised to the log base a, aren't they inverses of each other? Well, if they undo each other, then it will simplify to be x, or whatever that is inside. So those happen because they're inverses of each other. Yes, used in calculus. That was the one that she kept saying. The kids can't look at this and tell me that it simplifies that quickly. I'm like, what? Okay. All right, so everybody look. We just saw that if we had base 2 to the x equals base 2 to the 5, because they're both base 2, can't we just use our exponents to solve? Yeah. Well, then that works for logarithms as well. If we have log the base a of x equals log the base a of y, since they're both log base a's, just like these are both base 2's, if they're both base a's, we can just solve with the inside of our logarithm, x equals y. Because of the one-to-one property. Same as this one-to-one property. Same idea. Okay, let's test your ability to do basic properties of logarithms in 2 seconds each. Okay, so let's test you out. So it's these, really, you don't need to write these down, you're just going to answer them. Log to the base 4 of 1 will simplify to be? 0. Log to any base of 1 is 0, always, okay? What will this simplify to be? 2. Doesn't log base 3 and base 3 cancel out? Easiest thing you've ever seen. Base 6 raised to the log base 6 of 20. 20. They undo each other. That's what inverses do. Log to the base a fourth of 1 is? 0. Very good. Right here, log to the base root 7 of root 7 will simplify to be? 1. Because technically that's a 1 right there, isn't it? Yeah. And then they undo each other. Smiley face, log to the base smiley face of heart? Heart. So you guys get your basic properties of logarithms. Very good. See, logarithms are easy, aren't they? Whenever I hear people say they're hard, I'm like, then your teacher didn't teach it right because it's easy stuff. Okay, here we go. If I said to you, solve these simple logarithms. Look, log base 3, log base 3. So what can we do?
X equals 12.
X equals 12. You've just solved the logarithm. All right, what would be my true statement here?
2x.
Very good, and then you just solve. So subtract 2x, so that'd be 1 equals negative x, so doesn't x equal negative 1? Yes. Technically, yes. Okay. All right, what would be my true statement here? X squared minus 6 equals 10. So you'd add 6, so x squared equals 16, so x equals?
4.
Plus or minus 4. Very good. When solving and taking a square root, we need our plus or minus. All right, you guys did awesome. Okay, this is the last thing I'm going to let you work on the homework for a minute. So everybody look. We're going to switch back and forth. On the homework, it's going to say write the log as an exponential and an exponential in its logarithm form. So right here, what would be the true statement in exponential form? Base 3 to the 4th equals 81. Does everybody see how we're doing that so quick? We're just doing the math. Okay, right here, we would have log to what base? 8 of 64, right? Log base 8 of both sides, everybody. Picture yourself doing it. Equals 2. Does everybody know how to do it? Just the math, right? We log base 8 both sides. Log base 8, people. Those undo each other. We get our 2. Log base 8 is 64. Are we good? Alrighty then. Go to the homework and get some tackled. As many as possible. 1 to 29 on. Okay, so first of all, let's kind of get going with how we would potentially start graphing a logarithm. So let's build up. It says graph the function at its inverse. So everybody, here's the function and here's its inverse. Here's the function, here's the inverse. Well, what if they didn't give you that this was the inverse? How would you find it? So just a reminder, what we're looking at right here is y is equal to base 3 to the x. Do you agree with me? So that's my original function. To find an inverse, don't we first switch x and y? So that'd be x equals base 3 to the y. Now, how do we undo? We need it to be y equals, don't we? Isn't that how functions work? How do we get y by itself? We need to undo base 3. How do you undo base 3? So we log base 3, log base 3. So now look what we would have. Log base 3 of x, don't we? Equals y. And that's where the inverse comes from. Okay? All right. So now what you're going to do is it says graph the function and its inverse. So let's look at the original function to make an xy chart. It's an exponential base 3 to the x, so plugging in -2, -1, 0, 1, and 2 maybe. So 3 to the -2 is a 1/9. Do you agree? Then we have a 1/3. Any base to the 0 power is 1. If I plug in 1, I get 3. If I plug in 2, I get 9. So if I plot those points, -2 up a 9th, over -1 up a 1/3, over 0 up 1, over 1 up 3, over 2 up 9. Isn't this what my exponential looks like? Where's my horizontal asymptote? 0, right here. Okay. Because we know the more we plug in negatives, the closer and closer it will be. Now, to get the logarithms points, don't I just take those xy points and flip them? We don't need to do calculations with the logarithm. We just flip our xy points from our exponential. So we're going over a 9th, down 2 units. Then we're going over a 1/3, down 1 unit. Then we're going over 1 up 0. Then we're going over 3 up 1. And then over 9 up 2 units. So let's graph those points. Now watch me do it. Over a 9th, down 1, 2 units. Somewhere right there. Over a 1/3, down 1 unit. Over 1 up 0. Over 3 up 1 unit. Over 9 up 2 units. So let's connect the dots here. So if you had to guess, where would you say that asymptote would be?
0.
Out. Yep, it's at x equals 0. He's right. Because y is changing, but x isn't. Right, everybody? It's okay. Does everybody see how this would be now a vertical asymptote for logarithms? So exponentials have horizontal asymptote. Logarithms have vertical. All right, let's do now domain and range. So domain for an exponential function is always -infinity to infinity. Well, if that's true, won't the inverse's range be this one's domain?
Yes.
So this one's range is -infinity to infinity. Now look at the graph. That makes complete sense. It's going down and up forever, isn't it? Okay, let's look at let's look at the range of our exponential. 0 to infinity, not including 0. Well, then that must be the inverse's domain, which makes sense. Look at the graph here. 0 to infinity would be that one's domain, right? Now I want to point something out to you. With this being our logarithm graph, could I ever plug in a negative into the log? X is input. Do you guys see how we can't plug in negatives? It would be an error. Like if you tried to put in a logarithm in your calculator with a negative, inside the logarithm it's an error. It can't happen. Logarithms have a domain from 0 to infinity. So question for you. Could I do log to the base 3 of 0? No. Isn't there an asymptote 1, 0? Do you guys see how we couldn't do that? That would also be an error. You cannot plug in 0 into a logarithm. Can't plug in negatives, can't plug in zeros. Okay, awesome. So this one has a horizontal asymptote and vertical. Now what if I start shifting the logarithm? So we know exponentials, if we shift it up or down, that's what changed our horizontal asymptote. With a logarithm, a shift left and right will change our vertical asymptote. So then that will change things up. So let's look at how we would graph. Here are the steps. This is the only example I'm going to do because it's very straightforward. Here are the steps to graph a shifted logarithmic function. Everybody, you are going to follow these steps. I still have people, after I went over this first hour, they said to me, Ms. Christensen, how do I type that into my calculator again? Wait, no, you're not typing it into your calculator. You're doing it all by hand. So, how you're going to do it is you're going to say, okay, let's pretend this is a non-shifted logarithm. Let's take off all the shifts. Wouldn't that be y equals log to the base 3 of x, taking off all the shifts? Now, how do I get those xy points? Well, we hurry and write down the exponential. If it's base 3, wouldn't it be base 3 to the x? So write down the exponential's xy points, and that will help you get the logarithm's xy points. -2, -1, 0, 1, 2. So that's 1/9, 1/3. If I plug in 0, I get 1. If I plug in 1, I get 3. 5 plug in 2, I get 9. Now don't be mistaken, I always have people go graph that. You don't need to. We're using those to get our logarithm points, right? So now I'm going to switch them, and that will give me these points. So that would be over a 9th down 2 units, over a 3rd down 1, over 1 up 0, over 3 up 1, over 9 up 2. Does everybody see how now I have the logarithm's parent function points? Don't graph those still because we now have to shift those parent functions. Left 1, up 2. Shifting for all functions works the same. Isn't a left shift an x shift? Left 1, so we'll take our x's and we'll subtract 1 off of them. Then we're shifting up 2 units, so we'll take our y values and add 2. And then we will have our new x, y points, everybody. And those are our official points. Now, before I even get those points, because I went left 1, I used to have a vertical asymptote at 0, and now I've shifted left 1. My new vertical asymptote is at -1. I'll graph that before I even do my new x, y points. Alright, so now decimals are fine for graphing. 1/9 minus 1 is like -0.8. 1/3 minus 1 is like -0.6. 1 minus 1 is 0. 3 minus 1 is 2. 9 minus 1 is 8. Super straightforward. -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And then 2 plus 2 is 4. Now let's graph those points and see what's happening here. We're going over -0.8 up 0. So isn't that right there, roughly? And then -0.6 up 1 unit. So that'll be like right there. Over 0 up 2 units. Over 2 up 1, 2, 3 units. Over 8 up 1, 2, 3, 4 units. Now this is also what's funny to me. When on the test I see students go, think, okay, that's it. Is that it? No, it's just we don't have enough, we don't have more points. But doesn't it follow the asymptote and it does continue forever? Yes, so you gotta draw it out nice and pretty. This is the exact work that you should show and you would get full points. Like that's beautifully written out. I can see exactly the steps you took. Does that make sense on how to do it? Sweet. Now if I asked you the domain, it would be very easy to say -1 to infinity. True? And my range is -infinity to infinity. Okay, awesome. You guys are doing great. We're almost done here. Okay, let's look at what I call, so a logarithm with no base. Okay, we all know if we see the square root, it's really a secret 2. The 2 is not written, but it's there. Well, we have to know this. If we have y equals log to the no base of x, it is base 10 always. You just have to, it goes without being said, if there's a blank thing, it's actually a base 10, everybody. So that's one thing to know. Now remember, we saw exponentials e to the x last time. E is just an exponential function, roughly 2.7. It's just given a special name because it shows up so much, right? 2.7 shows up so much anyways in real world phenomena. So everybody, log the base e of x, they're not going to write log the base e. That is definitely possible. We can have log to any base. But they're going to give it a special name called ln. So ln and e go hand in hand. ln and e are inverses of each other. Because isn't log base e the inverse of base e? Yes, but we're going to call it ln because it's given a special name. So just remember, ln and e are inverses. E is the exponential form, ln is the logarithm form of e. So properties of logs also hold true for ln's, or natural logs. ln is the natural log, they just call it. So if you know properties of logarithms, you know properties of ln's. So let's look at some. If I said to you simplify, remember you should be able to do this in 1 second. E raised to the ln of 5 would be 5. Good. E and ln undo each other. 2 ln of e. 2, you're right, because this is e to the first. Does everybody see? E and ln undo each other. So 2 times 1 is 2. ln of e squared. 2. Very good. E raised to the ln of 12 would be 12. Properties of ln's are the same as logs. Pretty easy, right? Okay. Well, let's see if you can simplify these two. Let's see. Think for a second. Talk in your groups. Let's see who can think a little bit advanced. Not trick questions. Use properties of logarithms. Let's see if we got some answers. Once again, it's okay to be wrong. 100%. I just wanted to see if you guys could try to think a little bit. What did you get as an answer here?
-1.
-1. You would be correct because ln of e to the -1 is what we're technically looking at here, aren't we?
Yes.
And then don't ln and e undo each other.
Yes.
Yes, very good. Does that make sense, everyone? Now, let me ask you what the answer is on this bad boy.
0?
You're right, 0. How'd you get that? You're right.
Yeah. I kind of just like thought about it, and I was like, I don't understand. So I said 0 is always a good answer.
Okay. Yes. Say it out loud, you're right. Log to the base 2 of 1 is?
0.
So log to the base smiley face of 1 is?
0.
So log to the base e of 1 is?
0.
So if that's ln of 1 is? 0. Do you guys see what he's saying? This is ln, this is a logarithm. Logs to any base of 1 is 0. So that's 0 divided by 3, which is 0. Does anyone have any questions? Great, great thinking. I'm glad you guys thought. That's all I cared about. Awesome. All right, so what would the graph of an ln function look like? Well, everybody look, we could always graph an e function, which we know we have an e button on our calculator. We can plot points. If I said to you graph y equals ln of x, wouldn't you just take these e's and flip them if need be? All right, so an ln also has so we know e to the x has a horizontal asymptote at 0, so ln would have a vertical asymptote at 0. So what would the domain of ln of x be?
0 to infinity.
0 to infinity. So if I gave to you, this is more likely what you're going to see on the test. If I said y equals ln of x minus 2 plus 3, and I said find the domain, you don't have to graph it, what would you say the domain is without even having to graph it? Good, it was shifted right to, so now it's at 2 to infinity. Does everybody see why they're saying that? So our domain would be 2 to infinity, not including 2. Okay, great. Okay, now this is the last thing of the lesson. Write each in exponential or log form. So if it starts as a log, write it in its exponential form. So when you say to undo ln, I need to e both sides. So ln and e undo each other, so my true statement would be 2/5 equals e to the -0.916. Does everybody see? I've just rewritten it in its exponential form. This one, it says rewrite it in its logarithm form, so I'd ln both sides. So I'd have 2 equals ln of 7.389. Notice you're not solving anything, it's already solved. We're just switching back and forth. Pretty easy stuff. Do you agree with me? That's the end of the lesson. The rest of the time is yours. You have about 20 minutes.